Hello everybody, welcome back to another Gregorious Maths video. In this video, I'm going to be continuing my Homological Algebra series in a slightly different format. I have got some notes here, but some of what they say is partially nonsense, so instead I kind of transferred the good information on those notes to here, onto the board, partly because also I'm a little bit jaded, we could say, and for my ease and your ease, it's probably better if I don't have to write anything down. So this is, anyway, so yes, and so if you're early, you don't see the notes in the description, that is because I am amending them, so they might come out tomorrow. Anyway, what I'm actually talking about today. Today I'm talking about singular homology and cochain complexes. So singular homology is a generalization of simplicial homology, which was introduced in the introduction. So if you haven't watched that or don't have an understanding of simplicial homology, then I would very much recommend that you do watch that first. So I'll be generalizing simplicial homology to all topological spaces, and then making some more general remarks about chain complexes, cochain complexes, and chain homotopies and stuff. Just some more general, more exciting stuff that will set us up to do the real homological algebra shenanigans, which we'll be getting onto in later videos. So, let me proceed. First we have to go over singular homology. That is kind of unfinished business, so let's do that. So firstly we define the standard n simplex, which we denote by delta n. We define it as the set of all of these points in Rn plus 1, such that the sum of all the coordinates is equal to 1, and each of the coordinates is greater than or equal to 0. And so these are kind of like, this is kind of like an n simplex, standard n simplex with vertices, with unit vectors as vertices, I believe. I think is the interpretation. But this is the precise definition. And a singular n simplex is a map, a continuous map, from the standard n simplex into a topological space X. And these singular n simplexes, which kind of like deformations, continuous deformations of standard n simplexes, or I should say simplices, standard n simplices, these continuous deformations, these are going to be our tool for generalizing simplicial homology. Now, before I get on to the definition, I still have a couple more things, foundations I need to lay out. Firstly, the face maps. Now, if I ever get onto a series or even just a video talking about simplicial homotopy theory, for example, or even infinity categories or something, face maps are quite important. But for us, we just need to have them in our locker, kind of the definition in our locker. And what it is the ith face map. So we take an n-1 simplex and we kind of embed it into an n simplex by and each one of these embeddings is called the ith face. And all you do is you insert a 0 in the ith position. So t0 up until tn-1 maps to t0 up until ti-1, that's all the same. Then you insert a 0, and then you go ti and all the way up until tn-1. So it's all the same, you've just inserted a 0, so of course these conditions still hold, and you get an n simplex. And this is the ith face of the n simplex. And so the way we're going to define the boundary maps is we're going to take alternating sums of the ith face of an n simplex. But first we have to define the singular n chains in a very similar way that we did in the introduction. They're given by the free abelian group, which has the basis being the set of these singular n simplices. So it's a free abelian group, and the basis for this free abelian group is this set of all of these singular n simplices. And so this 4-part definition here is precisely what we need to define cohomology. And so we'll do that. The boundary map is given. So what we have to do is we need to go down a dimension, and what we're going to do is we're going to compose our singular n simplex with the face maps. And so to go down a dimension, we just look at the faces. Right? And by looking at the faces, we go down a dimension and we just take alternating sums of the faces. And in a similar way, if you've watched the introduction, we took alternating sums due to orientations and stuff like that. So how does this really work? Well, we've got an n simplex, like so, but we need to go down a dimension, so all we do is we just precompose with the ith face map, like so, and this composition is now an n-1 simplex. And so the boundary map is precisely given in this way. We map an n simplex sigma to an alternating sum of all of the ith faces. So you do an alternating sum of all of the faces of this n simplex, and you end up with an n-1 simplex. But the punchline is that when you do this twice, when you do the boundary squared, you always get 0, which is a key property, because now we can define singular homology to be the kernel of the nth boundary mod the image of the n plus 1th boundary. And so in this way, we've generalized simplicio homology, which again you can check out in the introduction. We've generalized it to singular homology. We've generalized it to any topological space now. We can take the homology. And so in this way, we've associated to any topological space an algebraic invariant, which is quite powerful, of course. And for example, in homotopy theory, that algebraic invariant would be homotopy groups. Of course, in kind of more traditional algebraic topology, it is precisely singular homology groups, or cohomology groups, etc., etc. And so, I feel the need to make a remark here, which Rotman points out in his text on homological algebra. And that remark is, firstly note that homology is a functor. So it takes in a topological space, gives me a group. That's the first thing to note. But we can decompose it further. Firstly, we can get a map from top to comp, where comp is the settable complexes, which we'll go over in a second. And this is basically the map which takes in a topological space and gives us these singular n chains and the associated maps and stuff. So a functor which contains all that information is a very geometric functor, and it gives us, from a topological space, it gives us a complex. Great. But we can go further. We can now, at this stage, once we've done that, we now transfer this information into algebraic information by taking homology. So we go from this complex, which we've gotten from a topological space, we get a complex, and then we take homology, and voila, we get a group. And this algebraic step here of taking homology is the object of study for us in homological algebra. And because this sort of procedure we can do this in algebraic geometry, we'll see sheaf cohomology. Now sheaf cohomology, we won't really ponder the algebraic geometry side of things, but we get a complex, And then we can study from there, using the tools of homological algebra, what is actually happening, what this functor is actually doing. And of course, by doing that, we get information about the original thing we were studying. So homological algebra consists of studying this half of the functor. So, why don't we begin our journey now? And our journey begins by defining exactly what a complex is. Because I haven't precisely defined it yet, although I'm sure you would be able to figure it out by yourself, given the examples that I've already told you. But, you know, I feel I should write it out. Now, there's two different types of complex, but they're pretty much just dual notions. So there's chain complexes and co-chain complexes. A chain complex is a decreasing sequence of modules and when I say, okay, we could have any abelian category. I'm just choosing modules because it's the standard example. But we could have any abelian category. Anyway, sequence of modules, Cn, and module homomorphisms, and they're decreasing, so they're going from Cn to Cn minus 1, Cn minus 2, blah blah blah. For on and on. And they satisfy the condition, just like this boundary squares to 0, these dn's have to square to 0. And respectively, a cochain complex is one which is increasing. So it goes from Cn minus 1 to Cn plus 1, blah 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 blah, or so on, so on, so on, such that d squared equals 0. So this property that d squared equals 0 is common throughout. And so of course we can study the cohomology or the homology of this chain complex in precisely the way you would expect, given this definition, is the quotient kernel mod image. Kernel mod image. The nth homology is the kernel of dn mod the image of dn plus 1, and dually the nth cohomology of a cochain complex is the kernel of dn plus 1 mod the image of dn. So this is precisely what you would expect, but this is just in more general algebraic terms, and of course this is just a special case. So, we've defined what a chain complex is. Now we're going to define related notions, or a property which you can study. We're going to begin to study this chain complexes, basically. And you might notice here that I've considered the complex as a category. But what are the morphisms, you might ask? I answer your question. A cochain map, we're just going to restrict ourselves to cochain complexes for now, because throughout this series we're mainly going to be dealing with cohomology anyway, so I'll just deal with, but of course everything is exactly the same for chain complexes. It's just easier to stick to one. A cochain map, F, between two cochain complexes, is a sequence of maps between the nth term of each cochain complex, which commutes with the differentials. If you want to be more precise, it makes the following square commute. And we can go even, so these are morphisms. We can go even further, and we can define two maps to be chain homotopic. If there's a sequence of maps Hn, which goes from Cn to Dn minus 1, such that Fn, so the nth map, F, minus Gn is equal to this, is equal to the n minus 1th differential on D, composed with Hn, plus Hn plus 1 composed with the nth differential on C. And this is quite a random definition, but we'll see that it works out perfectly in a second. So, okay. Sorry, I just need to close the door. I'll cut this part out. Anyway, back to the video. Okay. A chain map induces a map on cohomology. So this is already interesting. All it does is it maps the equivalence class of C bless you, to the equivalence class of f of C. Because when I say equivalence class, remember that these are quotients. This is kernel mod image. So the equivalence class of C maps to the equivalence class of f of C. Now we're going to see why chain homotopy works out so beautifully. If f and g are chain homotopic, then they induce the same map on homology. They induce precisely the same map, given that they're homotopic. So let me show you why this is true. So if we pick some element C in the kernel, so some representative of this equivalence class, and if we let H be some homotopy, then we'll just write it out. H, the nth homology of f at C is the equivalence class of Fn of C. Now, by this definition, we can just add Gn to both sides. So this is equal to the equivalence class of Gn of C plus this stuff. Now here's where the magic kicks in. This guy right here is going to be in Dn minus 1. And so when we compose it, when we pre-compose with Dn minus 1, when we compose this element here with the n minus 1th differential at D, well, we obtain somebody who is in the image of Dn minus 1. And therefore, because we're modding out by the image, this is going to be precisely 0. Okay. What about this? Well, we've picked a representative C, which is in the kernel. But it's... this is precisely 0 as well. And so this is 0 and this is 0. So the definition of homology is precisely working out so that we get the equivalence class of Gn of C plus 0. And that is just the nth cohomology, the induced map, on cohomology, which gets induced by G. And that's precisely the same thing. I also have in the notes a proof that homotopy is an equivalence relation, but I'll omit that for now. Again, I'll try and have the notes posted by tomorrow. And thank you guys for watching. I've tried to keep the energy high, despite my jaded state, my fatigued state. And yeah, hopefully I'll see you soon for Theorem of the Week, or even sooner maybe. Good day. Oh.